Hi, I made this video to help you understand how to approach the first lab, the trigonometry lab. So basically what we're going to do is just review your old skills from trigonometry, do a little bit of protractor work, and show you the basic measurements. To begin, some materials that you need a pencil. I would highly recommend something like a mechanical pencil, works really well for your markings. You need to have a protractor, something that's, I've actually, this is the one I could find around my house. A better one would be one that's clear plastic with the black markings. But you have a little more time. You should be able to try to see if you can acquire clear plastic's a good choice. This one you can see is kind of tough because you can't see the markings as clearly through the color. You also need, it says on the lab sheet, a 10 centimeter pencil, but I couldn't find a 10 centimeter pencil because I just don't really sharpen pencils that often. So I just found this little straight card. The main thing you need is a straight edge that's less than 10 centimeters, and the reason for that is because the protractor, if you could tell, the inner lining on this protractor is in centimeters, the outer lining is in inches, and the 10 centimeters is on the inside, so I'd rather keep something that's less than 10 centimeters so it's easier for me to measure with just a protractor and not have to have a separate ruler. So if you follow the instructions, the first thing it does is it says set the pencil at 37 degrees. So what we're going to do is first we need to set degrees, right? Well, to measure an angle, you need to have a some reference line, right? Because an angle basically is telling you the space, the opening between two lines. So this first thing we got to do is make a reference line, a line where we're going to say the 37 degrees is measured from. So take your straight edge, protractor or ruler, lay it down, make a nice sharp marking, right? Like so, and you should see a nice clear line. Yeah. Once you've got this nice clear line, next thing you're going to do is set for 37 degrees. So 37 degrees. The way you do that is you put the protractor on the line. You want to get it just exactly at the spot where you're going to measure this 37 from. Try to make sure it's as lined up as you can. Hard to do with this thing in the way, but as close as I can do it. And then I look on my protractor, I see 0, 10, 20, 30, 35, 37 is 3, 1, 2, 3 less right there, right? It's 38, 37. Right here. Make a nice clear line there. And then what I would do is I would just kind of like lightly trace out what that straight line is going to be, because that'll help with the rest of this when I'm laying down my item, right? So this here, now I've measured an angle here that is 37 degrees, so you might want to label that, right? Make your life a little easier. Next, I'm going to measure the R, the X, and the Y. So what the lab's saying is basically this guy, R, the R is for the resultant. It's kind of like when we talk about vectors, which you'll spend more time with it. It's like if I take x as A and y as B, R is like C in Pythagorean theorem, right? A squared plus B squared equals C squared. And conventionally, we use R very often for the resultant of two perpendicular vectors. So R is going to be normally what you probably called it in high school, the hypotenuse. So I take this, lay it down on the paper like so, and now I'm gonna make my life a little easier by getting it up to here, right? So I got a nice straight line that goes with exactly to where the edge of this object is, right? Cool, right? So I now know that the resultant is the measurement from here to here. I take my protractor or ruler, works either way, and when I look at it, I line it up like so, Oh, this one's going to be tricky because I can't actually see it directly. Maybe I can zoom in with the camera to see. This up a little bit. No, of course not. Why would I? That looks like 8, a little less than 8, so 9. That's going to be 8.8 centimeters, right? Zoom back out again, bud. There you go. 8.8 centimeters. So I measure the length of this to be 8.8 centimeters. And it was pretty much exactly on it, so I put 8.80 because 0 is the one I'm slightly unsure about. That's the last digit that I'm not 100% sure on, because it might be a little more. It might be 8.81 or maybe 8.79. There's some what we call margin of error in the last digit. It's like your last digit. You're not 100% sure that that has to be, you know, the correct number. That's why we have significant digits, right? So now we've got this, we know the long side, and then the next thing asks, that's going to be the R value, right, R. Next thing they want you to do is figure out the X and the Y, right? So the X, now this one what you want to do is you want to get a perpendicular so that you can clearly mark out where your X and the Y is. So the easiest way to make a perpendicular is take a protractor, line up it so that the 90 is on the line, then slide your protractor down a smidgen, actually a lot more than just a smidgen because I got to get it lined up there. So you want the perpendicular, the 90 here, and you want it so that this guy cuts right through like so. Right, that looks like it's 90. And then edge. Be as careful as you can. You want it to look as clean as possible. Take your time with it. There's no major rush. I mean, you got a week to do this, so should be straight, should be clean. And of course, I'm not a left-handed person, so I'm going to switch to my right hand. Try to keep this pushed down as best I can, and then along the line like so. Right. Now I've got a clear X and a Y, right? So my Y and my X, right? Measure with a protractor. Look in here, set the 0 so that it's at the point. It's 6.9. I want to say 6.9. Maybe 6.93. 6.93. And remember, this last digit is the one I'm not sure about, right? So 6.9, I know for sure, right? When I look at this on the protractor, right, that it's a little less than 7, right? It's slightly less. It's just like right in between the middle. And this is where we have the idea of uncertainty. I'm not 100% sure if it's 6.95, 6.99. That last digit I don't know within about a third of a millimeter. So I'm just kind of getting ballpark, and I know that the true answer is somewhere between 6.93 and then maybe 6.99 or something around there, right? So it's like got a margin of error. So we'll say 6.93 centimeters, right? The last bit here is my y-axis value. The y-axis, I'll do the same thing again, although you want to make sure your 0 is here, so put the 0 like so. Put the line up like here. Sorry, my head's in the way, so I'm trying to actually see this guy. This one's going to have more uncertainty because it is in a very bad position for how I'm doing this. There. Let's use the old camera and zoom around in. Alright. If I can zoom on in. And I don't block it. Yeah, I'm blocking my hands. That's great. Useful. Now ideally what you want to do is have your head directly above the measurement as you're doing this, and since I'm using a bit of a camera mount, it's a little offset, so it's going to be I got to kind of take into account that it's not going to be exactly perfect here. So that's 5 centimeters, 5.1, 5.2, let's say 5.22. 5.22. So we'll say this is 5.22, right? So zoom her back out again. Now once we've got, oh, don't always, you always have to have centimeters. That's the unit we're using, right? There's our centimeters. Okay, so we got our x, we got our y, we got our r. They want x squared plus y squared, which always helps if you have a calculator at the ready. And usually, well, looks like I'm going to have to use the computer calculator because I don't have one on hand. So, calculator. All right, so what we're trying to verify is, does Pythagorean theorem work for this case, right? So we're going to use x squared. So first write our formula, x squared plus y squared equals r squared. Oh, that's a y, right? So in this case, x is 6.95 centimeters squared plus y, which is 5.22 centimeters squared equals r squared. So that gives us 6.95 squared plus 5.22 squared. And that gives us a grand total of 75.55. 75.55. So 75.55 centimeters squared is equal to r squared. Now let's check that against the actual r, right? The actual r. So we want to check this versus the r that we measured directly. So the r that I measured directly is 8.80 centimeters. So the question now is, what is r squared? So we can compare it against the r squared we have up there, because that's what they're asking for, is the percent difference. So r squared is going to be equal to 8.80 centimeters squared. And then just throw that in the calculator, right? So 8.80 squared. 77.44. 7.44. So then the question is, what is the percent difference between these two numbers? Thankfully for us, they have the basic rules up top, which gives us that percent error. Is equal to the measured minus the actual divided by the actual times 100. What they're asking for in this case, though, is the percent difference, because in this case, our problem is we don't really know which one's the measured, which one's the actual, because in fact, both of these measurements are measurements. They're not actually, we don't have a predicted theoretical value. So what we really want to know is how close are these two numbers together. So rather than doing percent error, we're going to use percent difference. Percent difference. And for that, that's going to be equal to just the difference between the two values. So what we're going to do is take 75.55 centimeters squared. And we're going to minus 77.44 centimeters squared divided by the best of the two values, or the average of the two values. Well, which one is the best of the two values? Would we go with this value or this value? Or should we take the average? In this case, I would go with taking the value that we measured with only one measurement. And the reason for this is because every time you make a measurement, there's error in that particular measurement, meaning you're not 100% sure of that last digit for both cases, right? Like I wasn't 100% sure that that's a 5, and I'm not 100% sure that that's a 2. This one's got the same problem, but since it's only happening once, the error on this value should be lower. This value should have lower error than that value. So we'll use this as our best value. So 77.44 centimeters. And then we throw it in the calculator, right? So it's going to be clear 75.55 minus 77.44. Oh, don't forget the units. I've got a square in there, right? So the raw difference between those two values is 1.89 centimeters squared. The full value is 77.44 squared. So when I divide the two by 77.44, we get a percent error, or percent difference in this case. It becomes 0.024, right? But you have to times it by 100. So when you times it by 100, it's 2.44%. Yeah. And that's how you find, verify Pythagorean theorem, review it, and then how to get your two values, right? We used Pythagorean theorem to get a value. We took a direct measurement to get the value. I used the direct measurement as the better value, the one that I divided by, and then we get the percentage of 2.44% as the percent error, right? The lab has you do it a couple more times. You should be able to do that on your own. And that's the end of part 1. I will do part 2 ever so shortly. All right, for this lab, this is part of the lab. This is part 3. I just want to briefly show you what the procedure is. Although this one is very, very straightforward. I don't think there's anything major that you gotta deal with, but it doesn't hurt to just go over one more time. For part 2, by the way, it's pretty much the same thing as part 1. You just got to use different ratios, and I could probably talk to you through sine, cosine, all that kind of bit during the actual lab session. So what we're doing here is I'm just taking a piece of string, find some string somewhere around. I literally found some string I found on the same close tag I used for part 1. I just used the string, and so it doesn't have to be anything fancy. You just take the string, you want to wrap it around your circular object as best you can, like so. And this is not always going to be the most easiest thing to do, but it certainly is possible. And then once you've got it all so that the full length is there, what you want to do is take your fingernail or something like that and mark as best you can, although this is with a pencil, so real ugly marks, but that's okay. It's just giving me the mark on my string so I can remember exactly where the cutoff was for the circumference. So what we're going to do is first measure the circumference. Simple enough. We take our ruler, take the piece of string, line up the string at 0, and in this case I found my circumference to be 8 and change, 8.1, 8.2, 8.3, 8.4. No, that's 8.5, 6, 7. Yeah, it's somewhere between 8.8 and 8.7. I want to say 8.7. Yeah, I'll go with 8.7. Hard to see. So our circumference is equal to 8.7, let's say 7.0 centimeters. That's the last digit I'm pretty much guessing at, but it's in the ballpark of that. With the diameter of this quarter, that's what I used for my first circular object. You can use that, you can use other things. Same concept. Now this one, kind of hard to do directly on the ruler, on the quarter. What you want to do is you want to get it, because what we're measuring is the distance across the quarter. So what I would do if I was doing this to make it as good as possible, I would move the quarter until I get the maximum, because the maximum will be the distance across directly across the quarter. So gotta play with it a little bit, figure out where the maximum is. Should be halfway. So from my look and this particular ruler, I see 2.9-ish. Maybe, is it touching 2.9? I have to take it off camera to get a little closer to see it. It's like little. You also have to decide where you want to measure your diameter from, right? So the best place to measure it from is not the inner lip, is the outer lip. So you want, let's go to the very outer lip where it gets cut off. Try from there. I want to say it's 2.5 centimeters. It looks like that's exactly the production is 2.5 centimeters. Yeah. So we say the diameter is equal to 2.50 centimeters. Right? So I've got circumference, I've got diameter, and then to find pi, I know pi. Well, pi is, 3.1415 right? And it's not just 3.14. Pi is long, right? It's a irrational number. It goes on forever, and so it's kind of hard. You can't represent the whole thing on paper anyway because it's an infinite number of digits. But I would say if you went to just this 3.1415, that's probably a good enough representation for what we're doing, since our measurements are really only good to 3 digits. 3.1415 is more than enough digits to use for the expected value, because this is in fact what the expected value is, right? We expect pi to be this from theory, right? And this is the difference between the first part where we just use the better measurement and this part where we have an actual. So pi is the actual, right? And in general, the pi, by definition, for circles, is the ratio between the distance around the circle, the circumference, and the distance across the circle, the diameter. In this case, I measured my circumference to be 8.70 centimeters, and I measured my diameter to be 2.50 centimeters. And when I throw this in a calculator, we get 8.70 divided by 2.50. That gives us 3.48. So I find my ratio of pi to be equal to 3.48. That's my measured value. Right, and this, in fact, is not the real value. The real value should be this, and you can see why we have, the idea of percent error. So let's find out exactly what the percent error is, right? As always, percent error is just the measured minus the actual divided by the actual, right? So in this case, it's going to be equal to, that's percent error. All right, so in this case, it's going to be the measured value, 3.48 centimeters. Well, no centimeters actually. And the reason why there's no centimeters is because you have centimeters on the bottom, centimeters on the top. Centimeter divided by centimeter, they cancel each other out. 3.48 minus 3.14. And then this is 3.14 again. 3.1415. Let's use the extra digits since I memorized so many digits of pi. I memorized a whole 5 digits of pi. Might as well use what I can remember. So I take that 3.48 minus 3.1415. Although in your calculator you could just put in pi, and your calculator will give you all the wonderful digits it can remember, up to like, I don't know, 20 digits or something like that the calculator might have in it. I'm not 100% sure. So it's 0.3385 is the difference in the numbers. And then I divide that by 3.1415. Divide by 3.1415. That gives me 0.107, which we'll say gives us 11% error. That's pretty terrible. You know, and there's a couple of reasons why this error is pretty bad. For one, you're always going to have a lot of error percentage when you're using small distances involving, you know, a relatively large, what's it called, increments. Like, see this millimeter is actually relatively large compared to the size of the actual quarter. So any tiny off of my eyeball with this is going to make a much larger error. So you might want to, as part of your lab report, you're supposed to consider error and what are ways you could have done this to get a better percent error. You know, and I only measured it once. So if I'm only measuring it once, you know, I'm only taking that one measurement into account. That can lead to much higher measurements of error than you might say if you were measuring it many, many, many times. Or, for example, measuring a quarter versus measuring something that's super large, like a basketball with like a large, you know, very precise meter stick, or let's say a tape measure, like using a basketball, finding the circumference of the basketball, finding the diameter of the basketball, using a tape measure. That'll probably get you lower percent error too, because again, the main thing here is that when you're using tiny measurements with tiny objects with big measurement tools, you're going to have more problems than if you're, you know, using a bigger thing and measuring it. You'll have probably lower error under those circumstances. So I hope this was helpful, and best of luck with your lab.